Hello dear students, this is Devansha from LG Institute of Engineering and Technology from LG University. We discuss about the implementation of all logic gates in terms of mathematics in a binary way or in a digital way. We can consider this mathematics as a Boolean algebra. So our today's topic is Boolean algebra. Right? Earlier we defined our logic is nothing but the kind of digital logic is the underlying logic system that drives electronic circuit boards. The digital logic is manipulation of binary values through the printed circuit board that uses the circuit and logic gates to construct the implementation of computer objects. We use a kind of logic gates or different kind of modules. So those logic gates will make a specific digital module or digital circuit, and that circuit would follow a specific kind of algebra, and those algebra we define as a Boolean algebra, and that algebra we define as a Boolean algebra. There are certain rules we have to understand. Based on that, once we apply 0 and 1, the different operators will operate a proper function in a processor. So those kind of proper functions we define as a Boolean algebra. So here, some of the laws we have to learn in a Boolean algebra, and that is one of the law is called associative laws with digital circuits of gates, right? So this is like A plus in bracket B plus C, that is equal to, you can also define in bracket A plus B plus C. Same with the dot function. So if you have A dot in bracket B dot C, that is equal to A B in bracket with dot C. So that is easily, you can implement using this particular logic gate, where one of the first law you can see the A plus in bracket B plus C. So B plus C, that shows the OR function. So here you can use the OR gate, and later on you can implement A plus in bracket B plus C, and that's the same rule you can apply like in bracket A plus B plus C. Now why you can see here this kind of digital circuit? Because once you go with the truth table, if you do this A plus in bracket B plus C, that is equal to in bracket A plus B plus C, that the answer will be same. Now the same logic you can also apply with the help of the AND gate, right? Same way, the another law that is called the cumulative law. We all know that A plus B, that is equal to B plus C. In a Boolean algebra, same way A dot B, that is equal to B dot A, right? That is also implemented using the OR gate and AND gate, where you can also take the 3 inputs like A, B, C, and you can also put like 3 inputs of A, B, C, like A dot B dot C, that is equal to C dot B dot A. Like that way you can also implement this kind of commutative law, right? Another one is called distributive law, where A in bracket B plus C, that is equal to AB plus AC. Now the same function or the law you can also implement using the logic gates. You can see this B plus C into A. So you have a combination of OR and AND gate. So here you have a combination of AND and OR gate, and you will implement the function, it's AB plus AC. That same way, separately you can take AB dot AC by taking the AND gate, and finally you can use the OR gate. So it's nothing but just exchanging the plane of AND and OR gate, and you can realize same output Y with the help of this Boolean function. So there are certain detailed laws, like here you can consider the De Morgan's law. So one of the important laws that we can define as the De Morgan's law, where you can take the logic operators or logic gates of AND, OR and NOT all together, right? So one of the law of De Morgan's is the first law. You can see A dot B whole bar, that is equal to A bar plus B bar, right? Now same you can also implement using the logic gate. You can see here A into B whole bar, and that's the NOT gate. You can see here I have used a kind of AND gate followed by the NOT gate. So here you can see you have used AND gate then NOT gate. Whatever function you realize, same function you can also realize by taking the NOT gate first and then the OR gate. So AND NOT again is a combination with NOT OR. So this is also called invert OR gate. So I can consider this particular terminology is NAND, and NAND is defined as the invert OR gate. So always remember NAND and NOR, these two functions are more or less related with the De Morgan's law, right? Now the same law like A dot B whole bar, that is equal to A bar plus B bar, that you can implement and also verify with the help of truth table, right? So let's see this here. You can find this A dot B as such. There are two variables A and B, so we have a total 4 combinations: 0 0, 0 1, 1 0 and 1 1, right? We can do the dot function of A dot B, so you'll have, and that will follow the kind of AND gate or ending operation, which is 0 0 0 and 1, right? And again, if you take the complement of this, you consider this, the next column is the A dot B complement is exactly a complement of A dot B. You'll have 1 1 1 and 0, right? Likewise, you can see from the LHS side, you can see the A bar and B bar is nothing but the complement of A and B. And likewise, if you do A bar plus B bar, that is the ORing function, you can see here both the result of A dot B bar and A bar plus B bar are equal, right? By that way, you can also prove the De Morgan's law. So this is what a kind of AND and NOT combination. Same way you can also go for OR and NOT combination. So see, this is the A plus B whole bar, that is equal to A bar into B bar, right? So here, this particular logic gates diagram, you can also see that here the OR gate, and then you have a NOT gate. So that is equivalent to NOT gate and AND gate. So here NOR gate you can also call as a bubble AND gate or invert AND gate, right? So this is one of the second important law of De Morgan's law. So from that you can also verify that particular Boolean function with the help of truth table. You can see the truth table here, A and B. As such, there are two variables, so 0 0, 0 1, 1 0 and 1 1. This is the sequence. From that, A plus B, that is equal to 0 1 1 1. And the next function is A plus B whole bar. You can see exactly the complement of A plus B, right? The same way, A bar into B bar, you can see the complements of A bar and B bar, complements of A and complements of B. You can have A bar and B bar, and the dot product of A bar into B bar. You can see both the answers are equal. So from that, you have a 2 De Morgan's law is like A dot B whole bar is equal to A bar plus B bar, and A plus B whole bar is equal to A bar into B bar, right? So those 2 De Morgan's laws are related with NAND and NOT gate, right? So based on that, you have a complete chart of all the laws of the Boolean algebra, where you can see this particular table, the summary table. You can check. There is a first law is called the identity law, where 1 into A is always equal to A, right? So if you consider A is either 0 or 1, so you have a 1.0, answer is 0, 1.1, answer is 1, right? So it will always follow a parameter A, right? So 0 plus A is answer is always A, because if it's 0 plus 0, answer is A 0. If 0 plus 1, answer is 1 is A, right? So you can see this is kind of identity law. Same way you have a null law, that means A dot 0, answer is always 0. 1 plus A, answer is always 1, right? So this is called null law. Same way you can define more laws, like independent law is like A into A, that is equal to A, because it's a Boolean function, right? So 1.1 is equal to 1, 0.0 is equal to 0, like A plus A is equal to A, because 1 plus 1 is equal to 1 and 0 plus 0 is equal to 0, right? So wherever you have a variable A, B, C, anything, but just you put A is either 0 or 1 and you will get the answer. So from that you can see the inverse law is A dot A bar is equal to 0, because it's a multiply with the complement of each other. So this is A plus A bar is equal to 1, because it's a ORing function. Like commutative law, we have just discussed A dot B is equal to B dot A, and A plus B is equal to B plus A, right? Same way here we have associative law. So A dot B in a bracket into C is equal to A into bracket in a B plus C. Same with the ending and ORing operation, distributive law, we just have discussed A plus BC, that is equal to A plus B into A plus C, right? A in bracket B plus C, that we have seen AB plus AC, right? Then we have absorption law. Absorption law is just, we have A in bracket a plus b. From that, see, you can be able to get the answer by using the formula like a dot a plus a dot b. So from that you can take the common of a, where you apply the a dot a, that is equal to a from the independent law, right? From here you can see the function a plus ab, and we'll take a common, so 1 plus b. 1 plus b, that is equal to 1, so your answer is a, right? Same way here, you take the a common, so that is 1 plus b, answer is a. So the last one is the De Morgan's law, where you can just discuss about the De Morgan's law, where a plus b whole bar, that is equal to a bar into b bar, and a into whole bar, that is equal to a bar plus b bar, right? So you use this particular De Morgan's law, and from that you can apply a kind of simplification of all the Boolean function like a plus ab, that is, you apply all the rules and you can be able to get a plus a bar, that is equal to a. Now what is the importance? Main thing is, what is the importance? See, you have a large Boolean function, that means you have a large digital operations. Now from this large digital operations, if there are more number of variables, if there are more number of literals, there are more operators like plus, dot, not, gate, see, you require a more number of gates, right? So simplification of this Boolean function means what? See, the same output you can also realize with the least number of logic gates, with the least number of wires. So once you use this a plus ab, you can see a plus ab gate that requires two gates. One is AND gate and another one is OR gate. But once you simplify it, see, answer is a. So that means it's just a single straight wire that's required. From this, you can also check and verify with the truth table, where a and b, two variables, so sequence is 0 0 0 1 1 0 1 1. So a dot b is equal to 0 1 1 1. Same way, you have a plus ab, you can check the two equal columns like a and a plus ab, both are having the same answer. So you can straight away reduce your Boolean functions. By reducing your Boolean function, ultimately you are reducing the circuit parameters, or you are reducing the circuit size, you are reducing the logic gates, you are reducing the operations, right? You are reducing the time. So that's what you will get the fastest speed in a digital systems, right? One more example based on the simplification or reduction of functions with the basic logic gates AND, OR, and see, you can apply here a kind of De Morgan's law, where you can see a plus a bar into b, where a plus a bar into b, you can expand the a like a plus ab plus a bar into b, and once you expand this, see, ultimately your final answer would be a plus b by using this Boolean algebra. So a plus a bar into b you can implement with the help of three gates, AND, OR, and NOT, but at the end, see, you can consider that logic is nothing but the OR logic, right? So within a single logic gate OR, see, you can realize the output. So you can realize the same output as you can see like a plus a bar into b, right? From this truth table, you can check here in the truth table, a plus a bar b and a plus b, both are having the same answer. Based on that, we have more examples on this reduction of Boolean functions, and realize this basic gates like a plus b into a plus c. So ultimately you can go through the distributive law, and you further go for the simplification using the Boolean algebra. The final answer is a plus bc. Now you can check a plus b into a plus c. See, you require two OR gates, one AND gate, right? See, check this, two OR gates and one AND gate, right? But after the final realization of the Boolean function, the answer is a plus bc, right? So it's required one AND gate and one OR gate. So see, here we have reduced one logic gate. That's what our circuit becomes more faster, right, and much cost effective. And you can also check from the truth table where how you can simplify all the functions. So the basic idea behind this Boolean algebra, it's a kind of mathematics, is just to reduce the number of gates, just to realize and reduce the Boolean functions, right? Thank you, dear students.